Today, we are mastering a critical component of the higher level analysis and approaches syllabus, AHL 1.16, the solutions of systems of linear equations. In this lesson, you will learn how to solve systems with three unknowns using Gaussian elimination, how to interpret these systems geometrically, and how to classify their solutions. This topic is a staple of Paper 1 and Paper 2 examinations. It is important because it bridges the gap between pure algebra and three-dimensional geometry, often appearing in long-form questions where you must determine the nature of the intersection between three planes. Our goal is to ensure you can confidently navigate these matrices to achieve full marks. In three-dimensional space, a linear equation with three variables represents a flat surface called a plane. When we have a system of three such equations, we are essentially looking for the set of points where these three planes intersect simultaneously. The general form involves coefficients a, b, and c for each variable, set equal to a constant d. To solve this efficiently without getting lost in a sea of variables, we use an augmented matrix. Here is how the augmented matrix looks for our general system. Our primary tool for solving this is Gaussian elimination. The objective is to apply elementary row operations to transform the matrix into row echelon form, which we often call RREF. Row echelon form is achieved when we have zeros in the bottom left triangle of the matrix. Once we reach this state, we can use back substitution to find the values of our unknowns. Let us apply this to a system with a unique solution. Consider the system. X plus y plus z equals 6, 2x minus y plus z equals 3, and x plus 2y minus z equals 2. First, we represent this as an augmented matrix. Notice how the coefficients of the first equation form the first row. Our goal is to create zeros under the first element of the first column. We do this by performing row operations. This gives us this new matrix. Notice the zeros in the first column. To make the calculations easier, let's swap row 2 and row 3. Now, we have the swapped rows. To get the final 0 in the second column, we add 3 times row 2 to row 3. The matrix is now in row echelon form. We can clearly see the pivot positions. Now, we use back substitution. From the third row, we have negative 7z equals negative 21, which means z equals 3. Substitute z into the second row equation, y minus 2 times 3 equals negative 4, which simplifies to y equals 2. Finally, substitute both into the first row, x plus 2 plus 3 equals 6, which gives us x equals 1. The unique solution is the point 1, 2, 3. Geometrically, this means the three planes intersect at this single point. It is vital to understand that not every system has a single solution. We classify the results based on the final row of our matrix in row echelon form. If we have a full set of pivots, meaning we can solve for every variable directly, we have a unique solution. Geometrically, the three planes intersect at a single point, like the corner of a room. If a row simplifies to all zeros on the left but a non-zero constant k on the right, we have a contradiction. 0 equals k. This row takes the form 0, 0, 0, pipe, k, where k is not 0. This means there is no point that lies on all three planes. Geometrically, the planes could be parallel, or they could intersect in a way that forms a triangular prism where they intersect in pairs but never all three at once. If a row becomes entirely zeros, including the constant on the right, it indicates a redundant equation. The row is now 0, 0, 0, pipe 0. This means the planes intersect along a line or are coincident. We have an infinite number of solutions. Recognizing these patterns early in your row reduction will save you significant time during the exam. When a system results in a row of zeros, we have infinite solutions. To describe these solutions, we use a parameter, typically the Greek letter lambda. This allows us to write a general solution that represents every point on the line of intersection. Suppose we have reduced a matrix to the following row echelon form. The third row, 0 equals 0, confirms there are infinite solutions. We begin by letting our free variable, z, equal lambda. Next, we look at the second row, which represents the equation y plus 3z equals 5. Substituting lambda for z, we get y equals 5 minus 3 lambda. Finally, we use the first row, x plus 2y minus z equals 4. Substituting our expressions for y and z, x plus 2 times the quantity, 5 minus 3 lambda, minus lambda equals 4. Expanding this gives x plus 10 minus 6 lambda minus lambda equals 4. Rearranging to solve for x, we find x equals 7 lambda minus 6. We can now write the general solution in vector form. This is the preferred format for IB examiners, as it clearly shows the equation of a line in 3D space. Here, -6, 5, 0 is a specific point on the line, and 7, -3, 1 is the direction vector of the line. In Paper 2, where a graphic display calculator is permitted, you should not perform row reduction by hand unless specifically asked to show your method. The IB syllabus expects you to be proficient with technological methods to solve these systems quickly. There are two main ways to do this. First, the polynomial or simultaneous equation solver. Second, using the matrix RREF command. The most direct way is using the simultaneous equation solver tool. You simply input the number of unknowns, in this case, 3, and enter the coefficients and constants directly into the grid. Alternatively, you can define the augmented matrix as matrix A in your calculator. By using the RREF command, which stands for Reduced Row Echelon Form, the calculator will perform all the row operations for you instantly. If the system has a unique solution, the RREF command will return the identity matrix on the left, with your solutions x, y, and z in the final column. If there are infinite solutions or no solutions, the calculator will produce a row of zeros or a contradiction row, which you must then interpret just as we did manually. Always double-check your entries. A single mistyped sign is the most common reason for losing full marks in calculator active sections. Let's tackle an authentic IB-style question. Consider the following system of equations containing a parameter, k. Find the values of k for which the system has a unique solution, b, no solution. First, we set up our augmented matrix. We perform row operations to reach row echelon form. R2 becomes R2 minus 2R1, and R3 becomes R3 minus 2R1. Next, we eliminate the 1 in the second column of the third row. R3 becomes R3 minus R2. Now we analyze the final row. K squared minus 9 times z equals k minus 4. For a unique solution, the coefficient of z must not be 0, so k squared minus 9 cannot be 0. This means k cannot be 3 or -3. For no solution, we need a contradiction. 0 equals some non-zero number. If k is 3 or -3, the left side becomes 0. If k is 3, the right side is 3 minus 4, which is -1. 0 equals -1 is a contradiction. If k is -3, the right side is -7. So for no solution, k equals 3 or k equals -3. Wait, let's re-examine infinite solutions. This requires the entire row to be 0. For the left side to be 0, k must be 3 or -3. But for the right side k minus 4 to be 0, k must be 4. These cannot happen at the same time. Therefore, there is no value of k for which this specific system has infinite solutions. To secure a grade 7, you must avoid these 3 frequent pitfalls that cost students marks in IB exams. The most common mistake is a simple arithmetic slip during row operations. For example, when calculating row 2 minus 2 times row 1, students often forget to distribute the negative sign to the constant term at the end of the row. Always double-check each element individually. Students frequently swap the conditions for no solution and infinite solutions. Remember, 0 equals 0 implies infinite solutions. 0 equals k, where k is not 0, implies no solution. Think of it logically. 0 equals 0 is a true statement that doesn't restrict your variables, whereas 0 equals 5 is a physical impossibility, meaning no point can satisfy the equations. When a system has infinite solutions, students often stop after finding the row of zeros. The IB requires you to provide the general solution using a parameter like lambda. Failing to define z equals lambda and expressing x and y in terms of lambda will result in the loss of several accuracy marks. Being mindful of these will keep your work precise and examiner-friendly. To maximize your score in the AHL 1.16 topic, keep these exam-focused strategies in mind. First, always show your row operations explicitly using standard notation, such as row 2 becomes row 2 minus 3 times row 1. Even if you make a calculation error, clear notation allows the examiner to award method marks. In IB Mathematics, the method is often worth as much as the final answer. Secondly, be prepared to describe the geometric relationship. If the question asks to interpret the result, don't just say no solution. Instead, state that the three planes have no common point of intersection. If there are infinite solutions, specify that the planes intersect along a line. In paper 2, use your GDC immediately unless the question says, show that, or hence. Inputting the matrix into the RREF function is the fastest way to verify your work. If you are solving a system with a parameter like k on paper 2, you can even use the solver for specific test values of k to check your logic. Finally, if you have time, substitute your final values back into the original equations. If x, y, z work for the first two but fail the third, you know there is a mistake in your row reduction. It is time to test your understanding. Please pause the video and attempt these 3 questions. The easy question asks you to solve a system using Gaussian elimination. Here is your system of equations. For the medium challenge, determine the value of m for which the system is inconsistent. Recall what a row of zeros implies for the constants. The hard question requires finding a general solution, implying there will be a parameter in your final vector form. Take your time with the row operations. We will go through the solutions shortly. Let us look at the solution for the easy problem first. We represent the system as an augmented matrix. After performing R23R1 and R3-2R1, we get this matrix. Subtracting R2 from R3 gives us the row echelon form. Through back substitution, we find z is 5 over 3, y is 2/3, and x is 1. For the medium problem, we set up the matrix with the unknown constant m. Reducing the first column, we obtain a new matrix where the second and third rows start with 0 and -3. Subtracting R2 from R3 gives the final row as 0, 0, m-2, and 1. For the system to be inconsistent, the final row must represent 0 equals 1. Therefore, m-2 must equal 0, so m equals 2. Finally, the hard problem, which involves checking for dependence, reducing the matrix gives 2 identical rows. R3 minus R2 produces a row of zeros, indicating infinite solutions. Let z equal lambda. From R2, 3, y minus 5 lambda equals -9, so y equals 5 lambda minus 9, all over 3. From R1, x minus y plus 2z equals 5, substituting gives x equals lambda plus 6 all over 3. The vector form is the vector xyz equals the constant vector 2, -3, 0, plus lambda times the direction vector 1/3, 5/3, 1. To wrap up, use row reduction to reach row echelon form. Identify if there is a unique solution, no solution, or infinite solutions based on the final rows. For infinite solutions, parameterize the variables. Always remember the geometric meaning of these intersections. To summarize our lesson on the solutions of systems of linear equations, Gaussian elimination is our primary algebraic tool. We use elementary row operations to transform an augmented matrix into row echelon form. which allows for systematic solving through back substitution. Systems are classified by their final row in row echelon form. A full set of pivots indicates a unique solution. A row of zeros on the left with a non-zero constant on the right indicates an inconsistent system, and a full row of zeros indicates a dependent system with infinite solutions. Algebraic results have direct geometric meanings. A unique solution represents three planes intersecting at a single point, while infinite solutions represent intersection along a line or coincident planes. When infinite solutions exist, we must express the variables in terms of a parameter, usually lambda, to define the line of intersection in 3D space. In the exam, prioritize showing your row operations clearly to secure method marks, and always utilize the reduced row echelon form function on your calculator for paper 2 questions to ensure accuracy and speed.